Well, thank you very much. Thanks to the organizers for having me. It's so nice to be here. Today I'm going to talk about a recent work with Toby Hall. It's about multicurves on surfaces. So here is the outline of my talk. Well, let me first say that, as you all know, multicurves have played a central role in the study of mapping class groups. And two fundamental questions regarding multicurves on surfaces is to find an algorithm that determines whether a multicurve is connected or not. And if it's not, counting the number of connected components of a multicurve. And the second question is, given two multicurves on a surface, computing the geometric intersection number of these two multicurves. So that's what I'm going to talk about today. And well, there are algorithms. Schaefer, Sedgwick, Stefanekovich, Bell, and Webb use ideal triangulations of surfaces. They look at the number of intersections on the edges of an ideal triangulation and give polynomial time algorithms. Polynomial in the early characteristic of the surface and log of m, where m is the normal, the sum of the normal coordinates of the multicurves. And there are also, and they compute the geometric intersection number of multicurves. And there are also algorithms for counting the number of connected components of a multicurve. House and Susskind have a paper. They use measured train tracks and they compute the number of connected components of a multicurve on a genus 2 surface. And Dynnikov and Wist use interval identification systems, which is more suitable for comparing geometric and algebraic complexity of braids. And our algorithm uses Dynnikov coordinates on the punctured disk. So throughout the talk, our surface will be the n times punctured disk. And we're going to use Dynnikov coordinates. Normally, you can use Dehn coordinates or train track coordinates to coordinatize curves, but Dynnikov coordinates are particularly helpful coordinates when you work on the n times punctured disk for solving such combinatorial problems. And then I'm going to, and it was introduced by Dynnikov in 2002, and I'm going to also describe the action of the mapping class group in terms of these coordinates, and these are the two main ingredients of the algorithms I'm going to give today. So that's what I'm going to do. Another thing that I should note here is that the algorithms I'm going to talk today are entirely expressed in terms of Dynnikov coordinates. They only use Dynnikov coordinates, so you're given a bunch of numbers. These numbers will coordinatize your multicurves in a unique way, and you're going to look at those numbers, apply only 5 arithmetic operations, you know, adding, subtracting, comparing, taking the maximum and minimum, and that's all. And then you'll count the number of connected components of the multicurve corresponding to those numbers. And you're going to compute the geometric intersection number in a similar way. So the numbers will give you the answer. And there's also CUMPLIDO'S relaxation algorithm, which also can be used to count the number of connected components of a multicurve. That's also using Dynnikov coordinates, but experimentally it is lower than our algorithms. But on a theoretical basis, all these algorithms have the same complexity. And we're going to use her algorithm to compute the geometric intersection number of multicurves. Okay. So we have a multicurve that's a disjoint union of essential simple closed curves to homotopy. And essential here means that we don't have any curve which bounds a puncture or which is boundary parallel. So this is an example of a multicurve on the, well, in this case we have 1, 2, 3, 4, 5, 6, 7, 8 times punctured disk. And we take a standard model of the punctured disk where the punctures are aligned in the horizontal diameter of the disk. This is our model. And we take 3n-5 edges embedded on the surface. Some of these arcs are joining the punctures to the outer boundary of the disk, and some of the arcs are lying between two punctures. And these arcs divide the disk into 2n-2 regions, and 2n-4 of these are triangular when you identify the outer boundary of the disk with a point. So you can see This region is bounded by alpha 3, alpha 4, and beta 3, as an example. And we take a minimal representative of the multicurve with respect to these arcs, means that the multicurve doesn't form any bigons with these arcs. That's what we do. And then we count the number of intersections of the minimal representative of the multicurve with these edges. And this gives a set of integers, and which we call the triangle coordinates of the multicurve. Now the problem about these coordinates is that it's good, it's an injective map, but it's not surjective. For instance, if you concentrate on these numbers, this number of intersections on these edges, and if you glue up the pieces corresponding lying on these edges, if you glue up them together, it might be that you have some some curves bounding the puncture, or which is, boundary parallel. In this particular example, the number of intersections of the minimal representative of a curve system is given by 2, 1, 3, 4, 3, 3, etc. And this curve system has this non-essential curve. So this triangle coordinate function is an injection, but it's not surjective. So what we do is, the metric is that a certain linear combination of these number of intersections give you a bijection, and that's called the Dynnikov coordinate function. So the Dynnikov coordinate function is taking a multicurve on the set of multicurve here. This is the set of multicurves on the n times punctured disk. It's taking a multicurve here and sending it to a vector of length 2n minus 4, and it's doing it in a unique way. So this is the function. And how does it work? So first, let me compute some Dynnikov coordinates. This is the multicurve that I have, and I want to compute the Dynnikov coordinates. So let me write this formula in case it might be helpful later. So we have AI, which is alpha 2i minus alpha 2i minus 1 over 2. And we have BI, which is beta minus beta I plus 1 over 2. Okay?
Sorry, I've already forgotten. So AI is, that's the difference between the top and the bottom?
Yeah.
Okay.
Yeah, these, right, so let me, okay. So this is, the alpha i's are joining the punctures to the outer boundary of the disk, and the odd indexed ones are above the punctures. Yeah. And, okay, so let me compute A1 for this particular example. If you look at the number of intersections on alpha 1 here and alpha 2 here, 7 minus 5 over 2 is equal to 1. So this is the first Dynnikov coordinates of the multicurve. If you compute B1, B1 is the difference between beta 1 and beta 2. The beta arcs are denoted, the dotted lines are the beta arcs here. And if you look at the difference between beta 1 and beta 2, the multicurve intersects beta 1 twice and beta 2 12 times. So 2 minus 12 over 2 equals minus 5. So these are the first two Dynnikov coordinates of this multicurve on the 8 times punctured disk. So this is how we compute the Dynnikov coordinates. Any questions so far? No. Okay. So if you compute the rest of the Dynnikov coordinates in a similar way, you get a vector of length 2n minus 4. Well, this number here is not coincidence. In fact, the Dynnikov coordinate function is a homeomorphism from the set of measured foliations on the punctured disk, on the n-punctured disk, to r 2n minus 4. You can use this coordinate system also to coordinate your measured foliations, which is very helpful in studying dynamics of surface homeomorphisms. Okay, so yeah.
Very stupid question. You just have, on this line, you have negative numbers.
Yes.
And in homeomorphism, you have non-negative numbers.
No. So if you look at the number of intersections, you would definitely expect them to be positive numbers. And what you do, when you have a measured foliation, the arcs of the triangulation are assigned a non-negative number by the measured foliation. That's right. But we're not looking at the measures assigned on the arcs of the triangulation. We're looking at the difference between the measures assigned on the arcs of the triangulation. So we're looking at this formula here.
Right. So is there a greater than or equal to 0 at the very last line?
This one?
No, down, 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 that.
Oh, here. Yes, you're right. Sorry about that. Yeah, it should be R2n minus 4 minus 0. Yeah. Sorry, it's a mistake. Okay, so it works smoothly. Okay, so we have a theorem. That's the inversion of Dynnikov coordinates. So somebody gives me a vector from this space, and I reconstruct the number of intersections on alpha and beta arcs, and hence the multi-curve looking at this number using this formula. So this is an example of what this theorem does. We have a vector here, and we compute the number of intersections on the edges. These are the number of intersections on the arcs of the triangulation. And then we glue up these pieces together, and we reconstruct our multi-curve corresponding uniquely to this vector. And I'm not going to give the proof of the theorem here, but I'm just going to write up a few ideas. And if you use these ideas, it's an easy exercise to get this formula. So let me write the basic facts about a multi-curve on the n times punctured disk in terms of Dynnikov coordinates. So first of all, so this is a local picture. Okay, or you could have something like this. Right. So the fact is that, first fact is that if beta 1 is known, then all of the beta I can be found because of this relation. If I know beta 1, I know beta 2, beta 3, beta 4, etc. I know all these numbers. I can compute all these numbers because of this equation. Well, the second fact is, should I write it? Oops, where am I going to write it? Maybe here? Or maybe there? The second fact is that the number of intersections on each beta I is greater than or equal to 0, and the number of intersections on each alpha I is bigger than or equal to the number of pieces that go around the puncture, which is given by the BI coordinates. And I'm going to talk about the geometric interpretation of these coordinates in a while. This is the smallest integer, which is not less than I over 2. And at least one of these inequalities is an equality. And the third fact is that alpha 2I sorry, is the maximum of beta I and beta I plus 1. So the triangle inequality should be satisfied in each region because we have triangular regions. But if you have two consecutive triangular regions, in one of those regions you must have an equality. That's what it's saying. So in this particular picture here, this is alpha 1 and this is alpha 2, and alpha plus alpha 2, if this is beta 1 and this is beta 2, this is equal to beta 1. This is what it's saying. So I'll skip the rest of the proof, but these are the main ideas to prove this theorem. Okay. Right, so, okay. So what I would like to do is I want to understand the action of the mapping class group in terms of these coordinates. And the elements of the mapping class group are represented by braids on the n times punctured disk. So we have braids, And each braid is just a sequence of Artin's braid generators. And an Artin braid generator here is the anti-clockwise interchange between puncture I and I plus 1. And therefore, sigma I inverse is the clockwise interchange of puncture I with I plus 1. And if I understand the action of a single Artin generator in terms of these coordinates, I can compute the action of a braid in terms of these coordinates. So that's what I'm going to do. So I have a curve, and my curve, I want to see how my curve changes under a braid, how the Dynnikov coordinates of the multicurve changes under an action of a braid. That's what I want to do. And I make use of a very well-known lemma, this trick here. Assume that these vertices, these are rectangles, and I have vertices here. Assume that these vertices correspond to the punctures on the disk. And I have a multicurve, which means that the components are simple closed curves. So I have non-intersecting curves, lying horizontally and vertically these rectangles. And I have two cases. And either I have pieces that go from A to B, or I have pieces that go from C to D. There can't be both at the same time because I have non-intersecting curves. And therefore, an immediate observation says that the number of intersections on the diagonals of these rectangles equals the sum of the number of intersections on the opposite edges. If you try to apply this lemma here, you make use of, making use of a second well-known fact, which says that the geometric intersection number is preserved under homeomorphisms. So instead of looking at the action of sigma I, instead of looking at the number of intersections of sigma I of L with the edges, here, that's what I want to do. What I do is I look at the number of intersections of L with the inverse image, with sigma I inverse of the corresponding edge. That's what I want to do. So I apply sigma I inverse on my edges, and I get a picture like this. And this gives two equations. Okay. If you adapt this picture to the picture above, you can see that alpha 2i minus 1 primed plus alpha 2i equals the maximum of ui plus beta I and alpha 2i minus 1 plus alpha 2i minus 2. And here, alpha 2i primed equals alpha 2i minus 2. Another fact which comes from the first picture is here. There is a line between, connecting these two punctures, and therefore what we have is we have ui plus beta I equals the maximum of alpha 2i minus 3 plus alpha 2i minus 2 plus alpha 2i minus 1. So when you write up these equations, if you make calculations, you will end up with a picture like this. These are a set of rules which we wrote up in the max plus semi-ring structure because they are more useful for computational reasons. These brackets here mean that each time I see a sum inside the bracket, I'm going to take the maximum of these two integers. So a plus b in bracket means take the maximum of a and b. A times b in a bracket means add a to b. That's what these rules say. And these rules also are very useful because they describe, they induce a piecewise linear action on the space of measured foliations. And therefore, when you are on the boundary of Teichmüller space, you have these integer matrices, and get those integer matrices from these rules when you write up everything in terms of Dynnikov coordinates. So this is a very useful, tropical description of the action of mapping class group in terms of Dynnikov coordinates. Any questions? Right. Okay, now we can come to our counting algorithm. The motivation for the counting algorithm comes from a very well-known fact on the torus and on the 3 times punctured disk. Everything is fine. You can count the number of connected components of a multi-curve using, the greatest common divisor formula. So if you're on the 3 times punctured disk, you look at the greatest common divisor of the Dynnikov coordinates of the multi-curve and count the number of connected components. But we don't have a similar formula when you increase the number of punctures. So what we do is we input the Dynnikov coordinates of a multi-curve on the n times punctured disk and turn it into a multi-curve which is ported on the 3 times punctured disk, and we also get a bunch of elementary curves which I'm going to explain. So I'm going to apply a sequence of moves in the algorithm. Those moves will either, the number of connected components will not change, we will see. And at the end of the algorithm, we will see a curve which is supported on the 3 times punctured disk where I can apply this formula. This is the goal of the counting algorithm. Fun. Okay, but before coming to the algorithm, I'd like to say a few more things about the geometric interpretation of Dynnikov coordinates. There are some notations. So these are how the multi-curves look like locally. So this is the case where bi is equal to 0. Remember that bi is the difference between beta I and beta I plus 1, and therefore if the number of intersections on beta I plus 1 is greater than beta I, it means that bi is greater than 0. In that case, we have some loops that go around the puncture, and they have endpoints on beta I plus 1. And I call them left loops because there is a left loop on the left-hand side of the puncture. And I have bi is smaller than 0. It is defined in a similar way. I have these loops that go around the puncture, but they have endpoints on beta I. And because these loops lie on the right-hand side of the I plus first puncture, I call these right loops. And here, I don't have any loops that go around the puncture. I only have some pieces that are lying above the puncture and below the puncture. Well, in fact, if you take a minimal representative of a multi-curve on the n times punctured, there are 4 things that can happen in such a region. This is the union of consecutive triangular regions. You either have curve pieces that go above the puncture, or curve pieces that go below the puncture, or pieces that go around the punctures. There are no other possibilities because your curves are non-intersecting, right? And in terms of the geometric interpretation of AI coordinates, well, AI is the difference between alpha 2i and alpha 2i minus 1. And if you take difference between AI and I minus 1, it tells you how the curves bend around puncture I and I plus 1. So here is the picture where there are loops around puncture I and I plus 1. Sometimes you have these curved pieces that have endpoints on alpha 2i minus 2 and alpha 2i minus 1. They look diagonal. And sometimes, like in this picture, you have curved pieces that have endpoints on alpha 2i minus 3 and alpha 2i. And in this case, AI, the difference between AI and AI minus 1 is greater than 0. But sometimes you don't have such pieces. You only have above components and below components. And there's a left loop about puncture I and a right loop about puncture I plus 1. And in that case, you have a simple closed curve, which contains in the region bounded by the beta arcs. And we call such curves elementary curves. And that's an important thing. There's an important terminology in our algorithm, an elementary curve. So an elementary curve is a curve which is symmetric with respect to the x-axis and which is bounding 2 punctures, 2 consecutive punctures. And the number of intersections with the x-axis is therefore 2. This is an elementary curve. Okay. Right. So the moves of the algorithm, the moves of the algorithm are entirely expressed in terms of Dynnikov coordinates, but I'm going to illustrate them geometrically. So filling in a puncture, well, this move is applied when there is a puncture with no loops around it. So if your multi-curve, this is a multi-curve on the 1, 2, 3, 4, 5, 6 times punctured disk, and you can see that there is a loop around punctures, the second puncture, but there is no loop around the third puncture. If there is a loop, if there is a puncture where you don't have any loops around, you can erase that puncture. So you fill in that puncture. When you fill in that puncture, you have the same set of simple closed curves. The simple closed curves do not change, but you have put your multicurve, the same set of multicurves, on an n-1 punctured disk, but you are in the n times punctured disk. So you've decreased the number of punctures by 1 by applying the filling in the puncture move. So what it does to the Dynnikov coordinates, well, you first of all, you erase the corresponding Dynnikov coordinates AI and BI. You shift one place to the left all the Dynnikov coordinates AJ and BJ, where j is greater than or equal to yi. But in total, the sum of the Dynnikov coordinates haven't changed. The sum of the absolute values of the Dynnikov coordinates do not change, but the number of punctures have decreased by 1. Okay, may I ask how much time? I'm gonna be
32 minutes.
32? Okay, cool. Right. So erasing elementary curves, you remember that an elementary curve is a curve which bounds 2 punctures and which is symmetric to the x-axis. If you look at this multi-curve, it has an elementary curve. What this move does, it erases elementary curves. So if there is a left loop about a puncture and a right loop about the consecutive puncture, and the difference between AI minus 1 and AI is 0, that means that there is no banding around here. There is an elementary curve, and the number of elementary curves is the minimum of the absolute values of the corresponding loop components. What this move does, it erases elementary curves. It erases the elementary curves, and it records the number of times that the elementary curves have been erased. So in terms of Dynnikov coordinates, what happens to the Dynnikov coordinates? Nothing happens to the AI coordinates, because elementary curves do not contribute to the AI coordinates, since the AI coordinates is just the difference between alpha to I and alpha to I minus 1, but it definitely contributes to the number of the absolute values of BI coordinates. So you have decreased the sum of BI coordinates by m, where m is the number of elementary curves. So this move decreases the sum of the absolute values of the Dynnikov coordinates. So there's some decrease in this move as well. And the untwisting move is the move, well, it is applied when there is a left loop about puncture I and left loop about puncture I plus 1, but there is no elementary curve bounding these 2 punctures. So there are two things can happen in this case. There are 3 pictures, but these 3 pictures correspond to 1 case, but 2 main cases is that if you untwist if you concentrate on the first multi-curve, you untwist your curve, and what happens is that at some stage, a repeated application of the untwisting move gives you a puncture to fill in. Or sometimes, if IAB, this is a different notation, but if IAB is the smallest I with I iota greater where, well, okay, let's keep it 0. If you define a function like this, then this move decreases I by 1. Sometimes you get an elementary curve, and sometimes you don't. So it decreases. It decreases I, certainly, like in both of these cases, but what you get at the end, either you get a bunch of elementary curves after this move, or you get nothing, but you have already decreased I by 1. So there's also some decrease in this move. Okay. Any questions about the moves or how they, yeah?
Can you say again which one you do? Because if there are several I mean, maybe you just said it, but if there are several I where this untwisting is possible, then which one do you do? You do the biggest or the rightmost? Or?
I take the smallest I with BI is greater than 0.
The smallest I, okay.
Yes, and yeah, that's all how the algorithm.
So that's sort of the leftmost.
Yes, that's right, the leftmost one. Yeah, that's right. Okay.
Would it speed things up to do the biggest one?
Yeah, that's how we picked, but we could have chosen, a different way of, untwisting but of course, I don't know how it would affect the complexity of the algorithm at the end, but okay. So, but of course we're not interested in the curves, but we are interested in the Dynnikov coordinates of curves. So this algorithm takes as input the Dynnikov coordinates of the curves and outputs the curves after these moves. So here is the counting algorithm 1. The algorithm works with a pair ABY. So AB is the Dynnikov coordinates of the multicurve. So there is a unique multicurve corresponding to this vector, and Y is the number of elementary curves that we've erased. We first extend coordinates, which means that we add 2 dummy punctures to the surface. This is for computational reasons and for helping, it helps us to make computations in an easy way. So the second thing we do after extending, we seek for the B coordinates such that BI is equal to 0. So if there is a puncture to fill in or not. If there is a puncture to fill in, we fill in that puncture. And after we fill in that puncture, it might be that we get a curve which is supported on the 3 times punctured disk. And we have a formula here to count the number of connected components of the multicurve. If the new lamination, if the new multicurve is lying on a surface where the puncture is greater than or equal to 3, is greater than 3, then what we do, we go to step 3. Step 3 is where we erase the elementary curves. So we check if there is some I such that the difference between AI and AI minus 1 is equal to 0, which means that there is an elementary curve somewhere lying inside the multicurve, and we erase that. What we do, we erase the elementary curves and record the number of elementary curves that we've erased, and we go to step 2. Otherwise, we go to step 4. I mean, if there is a puncture to fill in, we go to step 2. If not, we go to step 4, where we do the untwisting process. And the untwisting process has 4 possibilities in terms of Dynnikov coordinates. We look at the Dynnikov coordinates of the multicurves. We apply the right Artin braid generator to untwist the multicurve. And what we get at the end is either, as I told you before, after the untwisting process, either we get an elementary curve, and if we have an elementary curve, we go to the erasing elementary curve step. If there is no elementary curve, we get a picture like this, then there is a puncture to fill in, and then we go to step 2. And we repeat this process and finish the algorithm. But here is a geometric illustration of the counting algorithm, which is more clear. So we have a multicurve in this particular example, we are on the 6 times punctured disk. This is a multicurve, and we want to count the number of connected components of this multicurve. Of course, looking at the Dynnikov coordinates, but here is a geometric illustration. What we do, we extend the Dynnikov coordinate system. We add 2 dummy punctures on the surface, and then we seek for the smallest I such that BI is equal to 0. Well, in this particular example, there is no puncture to fill in because this is -3, this is -1, this is 2, this is -2, this is -2, and this is -2 in terms of BI coordinates. So none of them are 0. We don't fill in a puncture. And we also check whether there is any elementary curve or not. Well, in this particular example, we don't have any elementary curves. So what we do, we untwist. And how do we twist? We look at the smallest I such that BI is greater than 0. And the difference between AI and AI minus 1 is different than 0, which means that the curve is bending somewhere near puncture I and I plus 1. So in this particular example, if you look at A1, A2, A3, A3 minus A2 here, there is a left loop about puncture 3 and a right loop about puncture 4. And the difference between A3 and A4 is different than 0. So what we do, we apply sigma 1, sigma 2, sigma 3 inverse. Sigma 3 inverse takes this multicurve to a multicurve that looks like this. Now, this is a simpler multicurve. As you can see, we look at this multicurve and we ask the same question. Is there a puncture? Is there a puncture to fill in? Yes, there's a puncture to fill in. If you look at the third puncture, there's some puncture to fill in because the B coordinate is 0 here. So we erase that puncture, we get rid of that puncture, we fill in that puncture, and that gives us a new multicurve supported on the 1, 2, 3, 4, 5, 6, 7 times punctured disk. And we repeat the same process we untwist, we erase elementary components, and so on. And at the end, we get a multi-curve supported on the 3 times punctured disk, and we've already erased 1 elementary component, so this particular multi-curve has 3 connected components. That's what the counting algorithm 1 does. Well, in terms of complexity, it's quite a fast algorithm. This is showing examples which are done on a 100 times punctured disk. And for example, one of the dots, well, the x-axis here shows that all these numbers are millions. So this is not in fact 2,500. This is 2.5 million, 5 million, 7.5 million, and 10 million. The sum of the Dynnikov coordinates, the sum of the absolute values of the Dynnikov coordinates of the corresponding multi-curves equals 2.5 million, 5 million, 7.5 million, and 10 million, and so on. And the y-axis here tells us that this is 1 second, 2 seconds, 3 seconds, and 4 seconds. And if we concentrate on one of these dots in this cloud, for example, somewhere here, we have the total sum of running times of 100 randomly generated multi-curves with the sum of the absolute values of Dynnikov coordinates approximately 10 million. Well, it takes only 3.5 seconds to count the number of connected components.
How do you generate the random?
With multi-count command of Dehn, which I can show you after this.
Oh, yeah, you have a bijection. Never mind.
Yeah. Yeah. Well, the program can be found in Toby Hall software page. This is Dehn, which I've used for solving many problems, including dynamical ones, studying pseudo-Anosovs and measured foliations and other stuff. And well, in theory, this is a very fast algorithm. It is not competing with the existing algorithms theoretically, but in practice it looks much faster. And the fact that it's purely using Dynnikov coordinates, these numbers, and only using arithmetic operations that are applied on these numbers makes it interesting. And another thing, a footnote that I would like to talk about is that the Dehn also works for measured foliations now. A current version of Dehn also runs measured foliations. These algorithms are measured foliations, which could be helpful in studying, again, for example, reducible foliations. So it's an interesting thing to look at, to make experiments with this program. Okay, so this is counting algorithm 1. And as I mentioned to you, there is another algorithm, which is CUMPLIDO'S algorithm. That's also using Dynnikov coordinates. And that's also describing the action of the mapping class group in terms of Dynnikov coordinates. It has the same, what it does is, well, it takes as input the Dynnikov coordinates of a multi-curve on the n times punctured disk, and it outputs a positive braid, the shortest positive braid that relaxes the multi-curve. So what it does, it takes the multi-curve, well, the Dynnikov coordinates of a multi-curve, and it applies a sequence of R10 braid generators, and it gives this relaxed curve system, and with a positive braid, which is the shortest to relax the multi-curve. The relaxed multi-curve here means that a curve system where each component is symmetric with respect to the x-axis, so each component intersects the x-axis twice, and they might bound more than 2 punctures. So each elementary curve, for instance, is a relaxed curve. So you can always find a homeomorphism that takes an arbitrary curve system to a system of relaxed curves. And CUMPLIDO'S algorithm, if you concentrate on this algorithm once more, what it does, so she does is, okay, look at this. So this is A1, A2, A3, and A4 coordinates. So A1 is 0, -2, 2, and 0. These are the AI coordinates. And you check, you see that A1, A2, A3, A4. So A3 is greater than A1, A2, A3 is greater than A2 here. Yes, A3 is greater than A2 here, so she applies sigma 3. And then what she does is she checks these AI coordinates again. So here A1, A2, A3, and A4. So A2 is greater than A1, so she applies a sigma 2. And A1, A2, A3, and A4. So A4 is greater than A3, so she applies a sigma 4 generator here. A1, A2, A3, and A4. So A3 is greater than A4, another sigma 3, and another one, and she gets this multi-curve. So it's important to note that it's not the shortest braid that relaxes the multi-curve, but it's the shortest positive braid that relaxes the multi-curve. Okay. Right. So I got,
20 minutes.
oh, it's too much time because I'm almost to the end. So let me ask if you have any questions. Okay, so you don't? Are you sure? Okay. Yeah, it's always hard to explain these things. Okay, so, well, the CUMPLIDO'S algorithm has the same complexity as our algorithm. Theoretically, our algorithm seems much faster when we want to count the connected components of a multi-curve, but it's in particular helpful to compute the geometric intersection number of multi-curves. So the main ingredients of a geometric intersection algorithm is it's a simple idea. If you have two multi-curves and you want to compute the geometric intersection number of these guys, and what you do is you want to relax one of these curve systems. You want to turn it into a union of relaxed curves. That's what CUMPLIDO does, and that gives a braid beta. Now, we know that the geometric intersection number is preserved under homeomorphisms, so if you apply the same beta to the other lamination, the geometric intersection number of L1 and L2 equals the geometric intersection number of beta of L1 and beta of L2. So CUMPLIDO'S algorithm gives me beta. I apply the same beta to both of the laminations. One of the laminations, one of the multi-curves, is a relaxed curve system, and the other one is a complicated braid. So as long as you know the geometric intersection number of an arbitrary multi-curve with an elementary, with a relaxed curve, then you're done. So that's the idea of the geometric intersection number. Is it clear or? Yeah? So we have a formula which it's not an algorithm, it's a formula. It computes the geometric intersection number of a relaxed curve with an arbitrary curve. The idea is you take a representative of the elementary curve such that it intersects all possible path components of the, multi-curve. And then to obtain the geometric intersection number, you want to remove bigons. So you count the number of components of the multi-curve which forms bigons with the multi-curve. So here, in this particular example, what's the number of intersections? What would be your answer? What would be your answer for this particular one? What's the geometric intersection number of these two curves? What? 2, right? Because we do this. And how we do that in terms of numbers, in terms of Dynnikov coordinates, Dynnikov coordinates counts the number of path components which form bigons with the relaxed curve. And then we get 2. That's right. So here is the illustration. Here is the algorithm for computing the geometric intersection number of 2 arbitrary multi-curves on the n times punctured disk. We again work on the extended Dynnikov coordinate system. So we have 2 multi-curves. Well, in fact, we have the Dynnikov coordinates of these 2 multi-curves. And we find the braid which relaxes one of these multi-curves making use of CUMPLIDO'S algorithm. And we relax it. What we have is a braid that looks like this. And we apply the same braid to the other lamination, to the other multi-curve. And when you apply the same braid to the first one, you get a picture like this. So to be able to apply the formula which counts the geometric intersection number of a multi-curve with an elementary curve, you need to compute the Dynnikov coordinates and the alpha-beta coordinates. And the alpha-beta coordinates are obtained by the inversion of Dynnikov coordinates, which I showed at the beginning of my talk. So I compute the Dynnikov coordinates of this lamination, of this multi-curve. and the alpha beta coordinates, corresponding alpha beta coordinates from the inversion of the Dynnikov coordinates, and I have a formula, and that formula gives me the number of intersections. So the number of intersections of these two curves is equal to 20, making use of this formula. Okay, I think I'm sure I'm done. Thank you very much for listening.